In this example problem, we're going to solve for the displacement field, u of xy and v of xy, using using the strain field. So in this problem, we're given the strain field as epsilon x, epsilon y, and gamma xy. So we're given them as functions of x and y and some other known constants. We're also given the boundary conditions at our origin point for this plate. So we know that the displacement in the x and y is equal to 0, as well as the change in the displacement as a function of y in the x direction is also equal to 0. Right? So, so using this information, we can determine u of xy and v of xy. Okay? So we know that epsilon x was given to us as being equal to cy times L minus x. We also know that epsilon x is equal to the change in u of x of y with respect to x. So if we integrate this, what we end up getting is we would get CLX y minus CX squared y over 2 plus an integration constant. Now note the integration constant is a function of y, not a constant, because this is a partial derivative. Okay? So if you take the derivative of this function with respect to x, c of 1 of y would be equal to 0. All right? So in a similar fashion, we know that epsilon y was given as this. We can integrate this with respect to dy. If we do that, we'll end up with this function here, plus a constant that's only a function of x, okay? Or a function that's only a function of x, all right? And then our last one, we were given that gamma xy was equal to minus c plus d times a squared minus y squared. But we also know that it's equal to the sum of du, the partial derivative of u of xy with respect to y, plus the partial derivative of v of xy with respect to x. So if we take the derivative of u of xy, so if we take the derivative of 1, of equation 1 here, and we bring it down, we can solve for this integral here, right? And then we can do the same thing for if we use equation 2. All right, we can take the derivative with respect to x. All right. So the one thing I like to point out here is since c1 of y is only a function of y, we can simplify our partial derivatives to being ordinary derivatives for both of these terms. All right, so if we plug equations 4 and 5 into equation 3, all right, what we end up getting is this equality here. All right, so we can rearrange this equation to separate our variables onto each side. So we can have everything that's in terms of x on this side. Then on the other side of the equation, we can have everything that is a function of y on this side. All right, and then we can set all of these to a known constant e. All right, a known constant e. All right, so then we can solve for our two unknown functions, dc2 of x and dc1 of y dy. So we just rearrange these equations and so that everything is on one side. All right, and then we would just integrate them. So if we integrate them all, we get c2 of x would be equal to this function here, where we have an unknown constant j. In a similar fashion, we can integrate equation 8 with respect to y here, and we get c1 of y. where k is an unknown numerical constant. All right. So then we have three. So at this moment, the only thing that we don't have or don't know are these three constants, E, J, and K. Okay. So to determine what E, J, and K are, we can use the boundary conditions of the problem. Okay. So in the boundary conditions of the problem, we know that at x is 0 and y is 0, the displacement of the x is equal to 0. So that's our boundary condition. So if we plug in equation 1, we know that we'll get that C1 of 0 is going to be equal to 0. Using equation 2 and our boundary condition here, we found that C2 of 0 is equal to 0. And then using equation 4, you can know that dc1 of 0 dy is equal to 0. Okay, so these are our three new conditions that we'll use to solve for E, J, and K, all right, which are unknown constants. All right, so we can solve, if we plug equation 11 to equation 10 here, we can solve for K. All right, so if we do that, we end up getting K is equal to 0. If we apply equation 12 into equation 9, so you can use our new boundary condition here. We can solve for J. What we end up getting is J is equal to 0. And then our last one, in order to solve for E, we have to apply equation 13 into equation 8. If we do all that, we can solve for E as being equal to this term here. All right? So we now have E, J, and K. So we can now determine C1 of y and C2 of x. All right. So if we plug in E, J, and K into all these terms, we end up getting C1 of y is equal to this function here. And if we do the same thing for C2 of x, and we plug in all of our unknowns, we end up getting C2 of x is equal to this equation here. All right. So now we know C1 of y, we know C2 of x. If we go back to equations 1 and 2, the only things that we were missing were C1 of y and C2 of x. So we can plug in C1 of y and C2 of x into our u of x and our v of xy equations, and we can solve for, and we can write them all out. Okay. So all the terms, I know there's a lot of what appear to be variables in these equations, but remember that C, L, and D and A are all known constants. So we only have two variables. X and Y are the only variables here. All right. All right. So if you wanted to check, if you went through all this trouble to integrate everything, a great way to check your work is you were given epsilon x, epsilon y, and gamma xy. So you could take the derivative of u with respect to x to find epsilon x. All right, you could then take the derivative of the v of xy function with respect to y. And you could solve for epsilon y, and you could take the derivative of u with respect to y plus the derivative of v with respect to x, and you could solve for gamma xy. All right. So if your final solution, if you retake the derivatives and you get this the initial conditions, then you know that your problem solved. An additional thing you can do is you can plug in your boundary conditions to make sure they're true. So in this case, you had u of 0, 0 was equal to v of 0, 0 was equal to du dy of 0, 0 is all equal to 0. So if you plug in all of those should also verify that the boundary conditions are correct. All right. If they don't work, then you made a mistake somewhere in your integration, and you should go back and check your math. All right. So that concludes how if you're given a strain field, epsilon x, epsilon y, and gamma xy, and three boundary conditions, you should be able to solve for the displacement fields u of xy and v of xy.